Well, good evening. As I'm sure you're all aware, the Bible claims that people in the pre-flood world routinely lived to be 900 years old, and even after the flood, people often still were living for centuries. Skeptics have a hard time believing this. They like to mock it. It almost sounds like something like a late night TV infomercial, but the Bible presents this as sober history. And I'm sorry to say, but there are Christian apologists out there who are going around claiming that the ages of these Genesis patriarchs should not be understood literally. And I think that is dead wrong. And I think most of you watching this agree. Um, the Bible's a history book. It clearly is meant to be understood as history, and it's God's word. And since it is telling the truth about history, we would expect some people groups and ancient historians to possibly recall this longevity. And that actually turns out to be the case. The Jewish historian Josephus affirms that people once lived to be very old, and he cites 11 other ancient historians as corroboration of his claim. You have Augustine of Hippo, who also affirms that people used to live to be very old. And you have Native Americans who say the same thing. You've got that as well. You've got ancient documents like the Sumerians' Kings List. So there is some extra biblical, historical, or cultural confirmation of this longevity, but what about possible scientific confirmation? I believe there is. But in order to discuss this, we first have to answer a very important question. Do we think this longevity was natural or supernatural? I've always assumed it was natural. I don't think there's any biblical reason to suspect that it was miraculous or supernatural, and I think most Christians assume that as well. But if that's the case, you're almost forced to conclude that the same thing would have been true for the animals as well, because it is very difficult to imagine a mechanism or mechanisms for greater longevity that would have affected humans but not have affected animals. If it was genetic, fewer mistakes in their DNA, well, the same thing was true for the animals. If it's environmental, humans and animals are living in that same pre-flood world. So you're almost forced to conclude the animals too would have experienced greater longevity. And that raises the possibility that their fossils might provide confirmation for this. And so that's what we're looking at this evening, possible fossil confirmation for greater past longevity in animals. Now, of course, we are arguing that these fossils are from the flood. This is a very important point because we're going to be looking at fossils that evolutionists claim are millions of years old. And we vigorously dispute that. Okay, we affirm that these are from the Genesis flood. These fossils are found in water deposited sediments that later hardened into rock. You've got these rock units that cover enormous areas on the Earth's surface, spanning hundreds and even thousands of square miles, and even stretching from continent to continent. We simply don't see sedimentation like that occurring today. And my coworker, Dr. Tim Clary at the ICR, has written a book on this, detailing some of this flood evidence. We have good reason to believe that these sediments were deposited rapidly, not slowly over millions of years. Derek Ager was a British geologist and paleontologist. He wrote this 1993 book called The New Catastrophism. And in his book, he made it very clear that he did not think much of creationists. However, he argued that there are geological units like Sutton's Stone in Wales that, according to the conventional thinking, would have been deposited over millions of years. And he says, no, I think it was deposited in hours or minutes. And as creationists, we would agree. We think that's true for Sutton Stone and for all of these rock units from the flood. They were deposited very rapidly during the year of the Genesis flood. You've also got soft tissue in dinosaur and other fossils. This is very strong evidence that they did not live millions of years ago, because we know from well understood chemistry that these proteins in tissues cannot survive at reasonable temperatures for even 1 million years. So this is very strong evidence that these fossils are in fact from the Genesis flood. They're recent, and that includes the dinosaur fossils. They didn't live millions of years ago, rather they perished in the Genesis flood. Now, there was a post-flood ice age, and this is also very important. We've had a strong ice age model since the mid-1980s. Mike Ord, it was the groundbreaker who did the research on this. There would have been catastrophic flooding at the end of the ice age as the ice sheets melted, but you might have even had some catastrophic flooding during the ice age itself because of very heavy rainfall at lower latitudes. But in any case, you're going to get more fossils after the flood. And we know from Scripture that human longevity was still dropping after the flood, but it was still quite high. People were routinely living to be hundreds of years old after the flood, and that would have coincided with the Ice Age. Therefore, it's reasonable to suspect that Ice Age animal fossils would also show evidence of greater longevity. So we're going to be looking at both of those. And we're looking at direct fossil evidence as well as indirect fossil evidence. Now, we have to cover a little bit of background first. There are new fields of study called sclerochronology and skeletochronology, where paleontologists can count growth bands in hard body parts to figure out how old the organism is or how old it was when it died. And it's very similar to tree ring counting. They do this a lot with bivalves like clams and oysters, but to do it correctly, you actually have to section the shell and sacrifice the specimen. But they do this a lot. They've done many studies on bivalves. Now, when you do this, you can often construct a growth curve that shows how the organism's body size varies over time. And it will often be a length or height versus age. It often looks like this. This is the equation for that curve if you're interested. L naught is the size of the organism at birth or hatching, and L max is this final asymptotic adult body length, assuming it has determinate growth and reaches this maximum adult size. Now, the important point here is that when you get these curves, you will often have an interval of very rapid juvenile growth. Then the growth starts to slow down as the organism reaches adulthood. And then finally, once it reaches its adult body size, the growth stops. At that point, the organism might get fatter, but it's not going to get longer or taller. And so this is very typical. And there's two ways to construct these growth curves. The best way, the ideal way to do it is with a population of living organisms, whether living or fossil. So let's say you've got a population of oysters and you measure their body lengths and you count the growth rings in each so that you can get a graph of length versus age. And it is possible to construct an average growth trajectory that shows how this organism's body size changes over time. This is the best way to do it because when you have independent measurements, you can do a rigorous statistical analysis. But many times you may not have multiple specimens. You may only have a single specimen. And in that case, they will often still construct a growth curve for the creature. This isn't ideal, but it's nevertheless done a lot in these studies. So we're going to look at some direct evidence. Now, there's a couple of things we need to keep in mind here. We want to do, if possible, an apples-to-apples comparison. I would like to see growth curves for the same Genesis kind, both modern and fossil. That's what we would really like to do. That's the best case scenario. And of course, I'm sure many of you are aware that as creationists, we don't think the Genesis kind is equivalent to a species. We think it's broader than that, probably at the genus or family level. And so that means that if you have creatures in the same genus, uh, then they're probably the same genesis kind. Taxonomists have a tendency to oversplit and to assign really too many species names, but even if they are assigning them to the same genus, it's a pretty good bet they belong to the same genesis kind. Now, another thing you have to worry about when you're doing these examples is that creatures even today can experience extreme longevity if they're living in very cold water. For instance, you've got this well-known clam that can live to be 400 to 500 years old, but it lives in higher latitudes, and the same species at lower latitudes does not live as long. They think this has something to do with its metabolism being slowed down by the colder water. The Greenland shark is another good example of this. Now, you might that's something you got to worry about. Likewise, eating less may increase longevity, caloric restriction, and people have suggested that we might live longer if we ate less. Well, that kind of makes sense, I suppose. But these mechanisms are not adequate explanations for the examples we're going to be looking at, because in every example we're going to look at, evolutionists believe these creatures were living in warmer waters, if not warm waters. We've got some examples from Antarctica, but they believe that at the time, by their reckoning, the Antarctic waters were much warmer than they are now. We're also going to see that many of these creatures were very large. They were apparently well fed, so caloric restriction is not an adequate explanation. And something else was going on, and I think this something else has to do with that better pre-flood world before the flood. So let's look at some examples. We've got a living extant oysters and clams. Clams and oysters, they're still around today, but we can construct growth curves comparing the fossil and modern versions. One very good example of this is the genus Crassostrea. Crassostrea virginica is very popular. It's as a seafood. It's the eastern oyster. People like to eat it a lot. But you've got fossil versions with names like Crassostrea titan and Crassostrea gigantissima. Well, you can imagine that those imply that this fossil version was much larger, and it is truly remarkable how many species names for fossil creatures have connotations of giantism. This is Crassostrea gigantissima right here. Maybe you can't appreciate the size just looking at that right there. So here's a picture of me holding a giant oyster, and I'm not sure if it's Crassostrea gigantissima, but this gives you a feel for how big these giant oysters were. Interestingly, even evolutionists believe that Crassostrea gigantissima is almost certainly the direct ancestor of Crassostrea virginica. So in a creationist context, that means it's the same genesis kind. So let's compare their lifespans. ICR, we think the post-flood boundary is generally between the Pliocene and Pleistocene, although we think even some lower Pleistocene sediments could occasionally be from the flood. But in any case, regardless of where you place the flood post-flood boundary, again, we expect there to be evidence of greater longevity in both the flood and ice age fossils. So we're going to look at some. This is a summary of a graph that appeared in a 2001 paper where the author looked at 4 different assemblages of Crassostrea oysters. The first one here is a modern group, and the lengths of these curves are not arbitrary. They all stop at the maximum age that was recorded in each group. So in the modern group, none of them lived past 6 years. We've got an upper Pleistocene group, probably Ice Age. You can see they're living a little bit longer. Some of them live to be up to 9 years. And then you've got Miocene, which we think are from the flood, and they're living to be 20 and 23 years old. And I would hasten to add that these could be underestimates because these creatures would have been killed in the flood. Therefore, their true lifespan potential could have been much greater. And that's not the only example. You've got other examples from the eastern seaboard of the United States where the Pleistocene oysters are clearly living longer than the modern ones. This is a summary of some findings in this 2018 paper. You can see from Maryland that lifespans go down from the Ice Age to modern times. Same thing for Virginia oysters. In North Carolina, there's a little bit of a drop, but it's not nearly as pronounced. And there's evidence from the tropics, the American tropics, that the Crassostrea oysters were bigger. Those black squares represent oysters that on ICR we think would have been from the flood. And the other symbols represent more recent ones. And you can see that all stages of ontogeny for these juvenile Crassostrea oysters, the older ones, the ones we think would have been from the flood, are living longer, or they're bigger. Okay, and so it's not surprising that the final adult specimens would have been larger as well. This is summarized in a paper that was published at the Creation Research Society Quarterly. It's open access if you would like to read it, but that's not the only example. You've got the Pacific oyster, the giant Pacific oyster, Magellania gigas. Now, this graph right here came from a 2016 paper, and it was comparing Crassostrea growth curves. The largest one is called Crassostrea graphoides. However, the scientists have since relabeled that as Magellania graphoides, which is interesting because you've got another Magellania oyster curve right here. That's number 5, and you can see that the modern version of this genus is much smaller. It's not living nearly as long as the fossil version. So that's another possible example right there. You've got Glossymeris americana, the American bittersweet. And if you look from North Carolina, the modern specimens, none of them live past 10 years. But if you look at the early Pleistocene, you have some that are routinely living to be 30, 40, 50 years old, and one was thought to be 86 years old when it died. You've got the same species from Florida. There's not as much of a dramatic difference, although the early Pleistocene ones are living a little bit longer than the modern ones. Now, none of the modern ones are living past 10 years, but the early Pleistocene ones are living to be about 15 years old. However, the authors of this paper acknowledged that it's quite possible there could be very old specimens in Florida as well, but they just haven't found them yet. You've got the Mercenaria clam, the hard clam, and we see examples from North Carolina where they seem to have been living longer. If you look at the mid-Pliocene and early Pleistocene ones, they're living longer and they're bigger than the modern version. In Florida, it's not as pronounced, but the early Pleistocene ones are living longer than the modern and mid-Pliocene ones as well. But there are some contrary data. I'm generally expecting the fossil versions to be bigger, but in some cases that's not clear. Someone did a study comparing body sizes of Pleistocene and recent Mercenaria clams for the Gulf of Mexico. Gulf of America. There wasn't an obvious body size that I could tell. And also there are some recent ones that had quite long lifespans. So there is a little bit of contrary data out there. And I want to be upfront about that. But I think if you look at the big picture, we're seeing a clear trend where the fossil version are living longer. Here's a species from Japan. And these are growth curves from the mid-Pleistocene as well as 2 modern ones. And you can see that the body size and longevity are dropping as you move forward in time. Let's see, you've also got some that are extinct. Okay, we've got some extinct clams. Now, since they're extinct, we can't do a comparison with the modern versions, but nevertheless, some of these extinct clams were living to be very old. There were some studies done of fossil clams from Seymour Island at the tip of the Antarctic Peninsula, and they were living to be very old. These are Cretaceous. You can see some of them were living to be more than 100 years old. You've also got some from the Eocene. They too were living to be very old. And the scientists described this as extreme longevity, and they noted that it was very likely that even older specimens were out there either in the field or in private collections, but they just had not been found yet. You've got some very large bivalves like Inoceramus. Some people think Platyceramus platanus may have been a subgenus of this, and we do have a growth curve. We do have a growth curve for this. You could maybe quibble and say this is indirect evidence because we don't have the full growth curve, but we got a partial growth curve, and we know that some of these grew to be up to 2 meters long. And so you can use that to kind of fill in the blanks, and you can see this thing might have lived to be 120 years, and it would have probably still been growing even at 120 years of age. There are rudists that are thought to have had maintained high juvenile lake rates of growth over many years. Well, that is delayed maturation. If you extend that out, that's going to translate into greater longevity. And there are some other lower Jurassic bivalves that seem to show the same trend. And we've got partial growth curves for these. Again, these are not complete growth curves. We've got partial growth curves, but we also know that we have other specimens where we know the larger body sizes, and so you can estimate how long it would take them to reach those adult body sizes. And you can see some of them were living to be more than 150 years old. Also, they found evidence of a 200-year-old Antarctic ammonite also on Seymour Island. Now, it's a weird-looking ammonite. It doesn't look like a nautilus like most of them do. It's got a shell that looks like a giant paperclip, but they think it was more than 200 years old when it died. And the scientist, Linda Ivany, who's a leader in this field, she said, we just have to accept the reality of this extreme longevity in this animal. But that's not all. You've got evidence of extreme longevity in some very small Jurassic mammals. These are from the Jurassic. All creationists would agree these are from the flood. And we're looking at cute little guys like this, the genus Morganocodon. These are little bitty things, like the size of a shrew, very tiny. But they've got very tiny teeth, but they found a way to count growth bands in the cementum of the roots of these teeth, and they're using that to age them. And what they're finding is that some of them were living to be very old. They've got 7 that they think had very long lifespans compared to living mammals today. And you can see the colored squares. Those are the estimated lifespans, and these are minimum lifespans because again they were killed in the flood. But they're way, way, way above the modern trend line. Those little black circles are the lifespans of comparably sized mammals living today in the wild. And you can see there's a huge difference. And one Science News article said recent work has shown that the first mammals in the late Triassic and early Jurassic lived much longer than similar sized mammals today, up to 14 years old. If you compare that with today's shrews of similar body mass, some of which live to just over a year, this is a huge difference in lifespan. So that's direct fossil evidence. We've got some direct fossil evidence that these creatures were living longer, but we've got even more indirect fossil evidence. Now, before we get into the indirect fossil evidence, let's just take a breather here and catch our breath. You might be wondering, how on earth does a physicist end up doing longevity research? Well, I've been interested in giantism in the fossil record for a long time. And as many of you know, ICR, we're focusing heavily on biology right now. And for that reason, Dr. Galuza, our president, asked me to look into this, the subject of scaling in animals. Why are animals and animal body parts the sizes that they are. And I did that, and I kind of just, it kind of swerved into this subject of longevity because, believe it or not, there are connections. There's connections between adult body size and lifespan. And there's a physicist named Jeffrey West who's done a lot of work in this area, along with the biologist Brian Enquist and James Brown. And they've come up with this theory of metabolic scaling that basically assumes that the cardiovascular system is optimized. Now, unfortunately, they did not give the Lord Jesus credit for this. They claimed it was done by natural selection and evolution over millions of years. That makes absolutely no sense to me. And as many of you know at ICR, we are strongly pushing back on this paradigm of natural selection. We think it's a completely incorrect paradigm, and creationists have made a mistake by accepting it. But in any case, there are some interesting trends that show up when you study longevity in living animals and when you study this metabolic scaling theory. First of all, the metabolic scaling theory shows a connection between the time it takes you to become an adult and your adult body size. Larger animals take longer to reach adulthood. That's a general trend. Also, we just know, we know from general observation, okay, and also research in living animals, bigger animals tend to live longer. But we also know, and this is a strong trend that shows up over and over again, animals that take longer to mature, animals that take longer to reach adulthood generally live longer. So we've got these two big trends. Okay, we know that bigger animals generally live longer, and we also know that animals that take longer to mature tend to live longer as well. So what are we looking for if we're looking for indirect fossil evidence of extreme longevity? Well, two things we ought to be looking for are giantism and delayed maturation. That's what we ought to be looking for. Do we see evidence of these things in the fossils? Well, we do, and we're gonna see some examples here. But I want to give a shout out to these creation researchers of ages past: Donald Patton, Dr. Jack Cuozzo, and Greg Beasley. I would have included a picture of Greg Beasley, but I could not find one. But these men years ago recognized that there would be a connection between delayed maturation and greater longevity. And Patton and Beasley also suggested that there would be a connection between larger body size and greater longevity. So I want to give a shout out to these men because they were way ahead of the curve. And I think some of their predictions are actually, we've got data to confirm them now. So do we see evidence of giantism in the fossil record? Well, of course, we sure do. You've got giant fossil insects. You've got giant fossil turtles, giant fossil elephants, giant fossil camels, giant fossil kangaroos, giant fossil beavers, and the list goes on and on and on. We could spend hours on this, but you get the idea. Giantism is all over the place in the fossil record. And because bigger animals tend to live longer, that's an indirect argument for greater longevity. What about delayed maturation? Okay, is there evidence for delayed maturation? Yes, there is. And this gets back to counting of these growth rings and these hard body parts. You can do this in creatures besides clams and oysters. Fossil shark vertebrae are hard to come by, but occasionally you find some. And there are growth bands in the shark vertebrae that can be counted just like tree rings. Ditto for osteoderms in crocodiles and alligators. There are growth bands in the osteoderms that can be counted. And the criteria here for showing delayed maturation is not as stringent as showing direct evidence for greater longevity. We don't necessarily need the whole growth curve to show delayed maturation. All we need is really the juvenile part of the growth curve, or even part of the juvenile growth part of the growth curve. And if we can show that this creature was taking a very long time to mature, that's an indirect argument for greater longevity, even if we don't have the rest of the growth curve. Now, when you do this, you will often have to make estimates of body size. So it's a little bit harder than it is with bivalves, but there are allometric equations that you can use to estimate the size of a crocodilian or a shark or whatever. And they do this a lot. Now, when you do this, the growth curves can be somewhat herky-jerky because you're making these approximations. Don't let that scare you. You're going to see some examples where the growth curves are a little bit herky-jerky. That's to be expected, and we see that in the technical literature. All right, so what about giantism and delayed maturation in fossil fish? Well, we see that. The coelacanth, thought to long be a living fossil, it was found alive and well, off the coast of Madagascar in 1938. Actually, it is a living fossil. They thought it was extinct, but they found it. None of them, I don't believe, have ever been found that were more than 1.9 meters long. And I think the record is more like 1.8 meters. Recently, there was a paper showing they believe this thing has a lifespan of about 100 years. Well, guess what? You've got fossil coelacanths that are thought to have been 5 meters long. Well, how long was this thing living? You've got other giant fossil fish as well. But we've also got some even stronger evidence when we look at sharks. We've actually got some growth data from fossil sharks. One of these is the megalodon, the well-known giant fossil shark. This is a tooth, okay, a megalodon tooth. These things were enormous. And again, sometimes you've got vertebrae, shark vertebrae. And they did find a megalodon shark vertebra that has 46 evenly spaced growth rings. Now, the fact that they're evenly spaced is important because the spacing of the rings is thought to represent how much the body grows per unit time. So if they're evenly spaced, that means the shark is growing at a constant rate. And that means it's still on the linear part of the juvenile part of the growth curve. So you've got a 46-year-old adolescent shark, okay? And the authors of the paper tried to construct a growth curve for it. They didn't really trust the results, which is why they have that question mark pointing down. They had a similar. This is not their actual graph, but it's drawn after it. It's similar to it. But if you take the growth curve at face value, this thing might have taken 400 or 500 years to reach its adult body size. Now, a more conservative approach would be to say, well, let's just figure out the minimum time it would take to reach maturity. If you assume it had a body like a great white shark, it would have been just under 16 meters long. That's about 52 feet. And if you extrapolate the linear growth rate and you assume that each growth band is a year, you're looking at more than 89 years to reach maturity. And again, that is a bare bones minimum estimate because we know the growth has to slow down. It has to slow down. So it's going to be more than this. Now, to be fair, this is not airtight. Sometimes the growth bands, they are some cases where they know that some sharks can produce 2 growth bands per year, at least part of their lives. Other times you can have different numbers of growth bands in different vertebrae of the same shark. Now, some of this is related to the structure of the shark, where you have different parts of the girth or along the body are wider than at other parts. And so, admittedly, this is not airtight, but that's the assumption they normally make, and that's the assumption the authors of this paper made when they did their analysis. Now, not too long ago, they think they may have made a mistake, and that this really should have had a body like that of a lemon shark. And it would have been even bigger if that's the case, about 80 feet long. And so you can do a similar exercise. It changes the numbers a little bit, but it's still taken more than 70 years minimum to reach its adult body size. You've got the fossil shark Tychodus, which was relatively small for a fossil shark. It was only 10 meters long. That's about 32 feet. But you can do a similar, very conservative analysis. They think it had a body like that of a porbeagle shark. And if you assume that morphology, you can see that it would have taken about 63 years to reach that adult body size, and that is a bare minimum estimate. There are fossil sharks from Italy that they believe would have taken 64 years to reach 95% of its adult body length. Now, to put that number in perspective, great white sharks in the North Atlantic do so in about 33 years. So these are clearly taking a long time to mature in that, and these are large body sizes. Again, this is indirect evidence for much greater longevity. Now, I don't have any more shark fossil growth curves to show you, but we do have evidence, good reason to think, that today's sharks are the descendants of much larger versions of these creatures. For instance, the snaggletooth shark today, I think the longest one they have ever found was 12.5 feet, and that was an outlier. Most of them aren't that long. But you've got a fossil version of this genus that is thought to have been about 20 feet long. The same thing is true for thresher sharks. You have giant fossil thresher sharks, and their teeth have been described as highly enlarged versions of thresher teeth. You've got the blunt-nosed six-gill shark. The species name is Hexanchus griseus. Well, the fossil version is Hexanchus gigas, and of course that word gigas is derived from the word for giant. And you had some mainstream paleontologists who said they could not see any difference between the fossil and modern versions except for body size. So it looks like these sharks got smaller after the Ice Age. And of course, these are indications of greater past longevity. We've got an open access paper if you'd like to read more about it. Again, this is archived at the Creation Research Society website. But that's not the only example. We've got evidence of giantism and delayed maturation in fossil reptiles. For instance, you have the pterocrocs like Dinosuchus and Sarcosuchus imperator. You have replicas of their skulls in this museum here. And of course, that right there is an extant crocodilian. It's a bit of a pipsqueak compared to the fossil versions. And there was a growth curve that was published. And those dots there, those are the actual symbols that I was able to at least partially reproduce from a paper in Nature. But there was a smoothed version of this curve that was published later around 2004. Jack Horner was one of the authors of that paper, and they did not give the equation of the curve, but I was able to reverse engineer it. And so those are the parameters in your growth equation. And if you extrapolate this, it looks like it would have still been growing at even more than 100 years of age. Now, admittedly, extrapolation is always a little bit risky, but it looks like this thing was taking a very long time to mature. And by the way, the fact that it was already 50 years old is itself noteworthy because most crocodilians today don't live past 30. Yes, there are exceptions. Occasionally you will come across one that might be 70 years old, but most of them don't live past 30. So the fact that it was already 50 years old and still growing, and we know it could potentially grow more because you've got fossil versions that are thought to be even bigger. They're thought to be about 9.5 meters long. So this is pretty remarkable. And it's not just Dinosuchus. They found similar results for the Sarcosuchus imperator. And you might quibble and say, well, we're not 100% sure these are direct relatives of today's crocodilians. You know, they did have some unusual anatomical features, so maybe they're not crocodilians the way we think of them, and that's a fair point. But guess what? You've got fossil crocodilians that look suspiciously like giant caimans, and even evolutionary scientists describe them as giant caimans. They would say these creatures went extinct, but did they? Or did these giant caimans just get smaller after the flood with an accompanying decrease in lifespan? You've also got giant fossil gharials. They have these very distinct narrow snouts. Did they go extinct, or are today's gharials just smaller versions of these much larger, longer-lived gharials? We've got an open access paper on this if you'd like to read about it as well. Now, some people might object because it's long been claimed that large dinosaurs grew very quickly. Now, that's a little surprising for a lot of reasons, regardless of whether you're an evolutionist or creationist. But I think there are good reasons to question the claim that these very large dinosaurs grew very quickly. About 2001 or so, there was a growth curve for the T-Rex that was published, showing that it could supposedly reach adulthood in 25 years. And there was a growth curve for the Apatosaurus, claiming that it could reach maturity in 15 years. Well, that's really kind of hard to believe, frankly. This is one of the largest land animals that ever lived. You would think it would take a little longer than that to reach its full adult body size. Well, as it turns out, in 2013, a man named Nathan Myhrvold published a paper that was very critical of pretty much all published dinosaur growth curves. Now, Nathan Myhrvold has been described as the world's most curious human. He heads an organization called Intellectual Ventures. He was very critical of most of these growth curves, but there were some that he was not as critical of. And one of these was by a woman named Holly Woodward and her graduate advisor, Thomas Lehman. And they constructed a growth curve for Apatosaurus that is much longer. Now, the reason you have those multiple curves there is because the red ones are upper and lower bounds. The black one is kind of an intermediate value. You could get a good fit to either the later data points or the early data points, and that changes the numbers a little bit. But it looks like this thing could be taking, more than 100 years to reach its adult body size. And they did the same for 3 other sauropods. One of them looks like it might have been reaching maturity in 40 years, but the others look like they were reaching maturity at considerably greater ages. Now, admittedly, these are uncertain because we don't have a lot of data. You really have some, a small percentage of the growth data. But we know this thing is going to grow. We have estimates of their adult body sizes, and so you can use that to construct these growth curves. Interestingly enough, Nathan Myhrvold and Holly Woodward teamed up with Jack Horner and recently came out with a revised growth curve for T-Rex, where T-Rex would have taken 40 years to reach its adult body size. So I think there are very good reasons to question the claim that these creatures reached adulthood very rapidly. I don't think that's really plausible, even if you're an evolutionist. Bigger animals just naturally take longer to mature. That's not all. We've got evidence of giantism and delayed maturation in fossil birds as well. You've got giant fossil birds, you've got giant fossil penguins, but evolutionists themselves acknowledge that fossil birds apparently took a lot longer to mature than today's birds. Today's birds take a year or less to reach maturity. And the ones that take a year, those are the really big birds like ostriches and emus. Most birds today mature much more quickly, within weeks to months. And yet you've got fossil birds that are taking several years to reach maturity. Archaeopteryx is a good example. They've constructed a growth curve for Archaeopteryx, and they think it took about 2.7 years to mature. Now, there's considerably uncertainty in this graph because if you look carefully, you will see all we have are juvenile specimens. We don't have any adult specimens. Nevertheless, that's their estimate, 2.7 years to reach maturity. And you've got the same with large flightless fossil birds. I recently was a co-author on a paper where we summarized some minimum ages at maturity for large flightless fossil birds. And you can see there's a difference. The fossil birds generally take longer to reach maturity. And again, that's an indirect argument for longer lifespans. If you're curious, the fossil birds, the three far most bars are for what we think are pre-flood fossil birds. The next three are post-flood, but they're extinct. And the remaining five, those are extant, living, large flightless birds. Now, there's another piece of evidence that I think is extremely encouraging and exciting, and that's because in 2018, two evolutionary scientists published a paper suggesting that the reason no modern bird has true teeth is because the incubation times of modern birds are shorter than those of fossil birds. And in reptiles today, the embryos don't even start forming teeth till at least 40% of the incubation time is over. Now, I'm not saying that birds came from reptiles, okay, but let's suppose they had a similar growth schedule. What that means is if you have a shorter incubation time, there might not be time for the teeth to develop. There might be epigenetic switches that tell the developing embryo, hey, don't even bother trying to make teeth because you're not going to have time to do it. Now, if the fossil birds did have time to develop teeth, that would imply longer incubation times. And why do I get really excited about that? Well, guess what? Longer incubation times are also associated with greater longevity. So when we talk about age at maturity or time to maturity, we are not just talking about after birth or hatching, we're talking about before birth or hatching. So what is so cool about this is you've got what evolutionists have been using as proof of evolution. They claim the reason modern birds have true teeth is because, well, birds came from reptiles. Reptiles had teeth, but then they eventually lost those teeth over millions of years. There is another potential explanation. What they're claiming is evidence for evolution could actually be indirect evidence, indirect corroboration of extreme longevity in fossil birds, which is what you would expect given the extreme longevity described in the Bible. I don't know about you guys, but that gets me really excited. We've also got evidence of delayed maturation in fossil mammals. Remember these cute guys? Well, guess what? There is sufficient evidence to show that at least 4 of them took a very long time to sexually mature. Okay, those colored squares, those are estimated ages at sexual maturity. You've got there's some error bars. There's a little bit of a spread there, but you can see they are way above the modern trend line. The black dots are modern ages at sexual maturity for animals in the wild, and there's a huge difference there. I get real excited about this because this makes perfect sense in light of Genesis 5. Okay, Genesis 5, the earliest age at which a patriarch is listed as having a son is 65. Now, it doesn't say these are all firstborn. I suspect some of them were, but even if they're not firstborn, 65 is rather late in life to be having kids. And even, why don't we see ages at, say, 30 or 40 or 50? Well, I have a hard time believing that pre-flood humans were hitting puberty at 12 or 13 like today, and everybody was just waiting 30 or 40, 50 years to get married. I think that is highly unlikely, and I think this is a strong indication that pre-flood humans were also experiencing delayed sexual maturation. And that makes perfect sense in light of the fossil evidence we've got. Also, it looks like mammals got smaller at the end of the Ice Age. In fact, evolutionists have known about this for over 40 years. They've seen evidence. If you look around the land of Israel, that part of the world, it looks like animals got smaller. And there were a bunch of papers published even before this, where when you look at them as a whole, it looks like the mammals all over the world got smaller at the end of the Ice Age. Now, I don't care if you're an evolutionist or creationist. That's an important clue if you're trying to build a model of Earth history. But it's not just the mammals. It looks like other creatures got smaller too. Now, of course, this makes sense. Pre-flood the longevity in post-flood humans was dropping. It's a good bet animal longevity was dropping too. And since there's a link between body size and longevity, decreasing body sizes would kind of make sense. And we've got a paper on this. It's open access if you'd like to read it at icr.org or at creation.com. But it's not just the mammals. There's evidence that other creatures got smaller too. We've already seen evidence that sharks got smaller. The South African tick shell, people used to use it to make jewelry. Well, guess what? They were larger in the Pleistocene than in modern times. They got smaller over time. There's evidence that other South African creatures got smaller as well. Monitor lizards, it looks like they got smaller as well too. The gray monitor lizard there labeled 1, that's the Komodo dragon. 2 is the next largest of today's monitor lizards, but the ones labeled 3A and 3B are size estimates for Pleistocene monitor lizards. Okay, it looks like they got smaller too. And it looks like the giant clam got smaller. Tridacna gigas, that's the largest known living bivalve. The largest specimen they have is 4.5 feet across with a mass of 230 kilograms. Well, guess what? You have a fossil species, Tridacna gigantea, that's even bigger. One shell for a single Tridacna gigantea is 211 kilograms. Now remember, the largest known Tridacna gigas is 230 kilograms, but that's for both shells. And you've got one Tridacna gigantea specimen that they think was about 612 kilograms or so. It looks like they got smaller, and it looks like they were possibly growing more slowly during the Pleistocene than they are now. So we've got all this evidence that looks like creatures got smaller. And by the way, these are found in limestone strata. That's obviously from the flood. You find these in South Africa. But again, this is indirect evidence of greater longevity. So I hope this little talk has been an encouragement to you. As our former president, Dr. John Morris, used to say, it's a great time to be a Bible-believing Christian. And it really is. And I'm not, that picture of me is not supposed to be up there. Sorry. But it is a great time to be a Bible-believing Christian. In some ways, it seems like it's one of the worst of times because there's all this heresy and apostasy out there. And yet, we've never had more evidence corroborating what the Bible says than we do now. If you'd like to learn more, we've got some technical papers that you can access at our website, as well as a bunch of popular level articles. I know you've probably got some questions. So I'm going to try to anticipate some of your questions and do what I can to answer them. So let's look at some of these. I just know this one is coming. Do you think ancient humans were bigger too? I don't want to be dogmatic on it, but I got to tell you, I'm having a very, very, very hard time avoiding that conclusion. It seems almost inescapable. In fact, there are many ancient sources and historians who claim not just that there were giants, but normal post-flood humans were giants. There's a historian who claims that the people who made the Tower of Babel were giants, but they weren't Nephilim. These were normal post-flood humans. There's a tradition, a Scandinavian tradition, that Noah and his wife were giants. The Native Americans, we'll get back to that here. Some of them claim that their ancestors were giants. And I'll give you an example here. The Shawnee. This is a quote from about a Shawnee tradition. They, the Shawnee, suppose their ancestors have been much more perfect, both in intellectual and bodily formation, than the present race. They were a very large stature, both men and women, attributed in part to their abstinence from sexual intercourse during the early years of life. Now, that's interesting. That sounds like that could be delayed sexual maturation. In those days, the men at 100 years were equal to those of the present race at 70. A gradual degeneration has at last brought them to their present state and is now working imperceptibly among all the Indian tribes. And of course, it wouldn't be just the Indians too. And I think the same thing's happening to all of us. But this would be another indication that our ancestors may have been bigger. I think it's hard for me to avoid that conclusion. There's a rabbinical tradition that Adam was a giant. And of course, the size they have for him is ridiculous. But a lot of people think that. In fact, Augustine of Hippo said the same thing. He said people used to be bigger. He said the Nephilim, they were bigger than everybody, but ancient humans were bigger than we are. And what I find fascinating is that you hear talk from modern mainstream paleontologists talking about giant humans during the Pleistocene. And now, to be fair, if you go to his website and read what he wrote, he says, well, yeah, there were some really big humans in the mid-Pleistocene, but I don't think they necessarily were all big. Okay, that's fair. But the very fact that he's asking that question is interesting. Lee Berger, now I know Lee Berger exaggerates, so you have to take what he says with a grain of salt. But in an interview, he said one of the most interesting things that the fossil record reveals is that we went through a period of extreme giantism. There were people routinely 7 feet tall. They were huge. This was before we turned into the modern humans of today. So when I read statements like this, I wonder, what do these guys know that I don't? So I think it is very likely. I don't want to be dogmatic, but I'm having a very hard time avoiding the conclusion that ancient humans were bigger as well. What about contrary data? Well, I mentioned the Mercenaria clams. I haven't really found a whole lot of contrary data on longevity per se, but I have found some on body size, where it's not obvious that there's a body size difference between the fossil and modern versions. And you could argue, I mean, well, where are the giant human skeletons? That you could argue that's contrary data to what I'm arguing. Of course, we all know, we all know there's these stories about the Smithsonian, and I wouldn't bring it up except you may have to address it. I may have to address it because that's a potential objection to what I'm saying right here. Is there reason to think that there's fossil evidence that's been ignored or explained away? As creationists, we kind of sometimes want to tiptoe around that, but when you're getting into this subject right here, you may not be able to. Some other possible contrary data, mammals, it's kind of all over the place. Even the evolutionists say the data are contrary. What about further research? Well, one thing I'm very interested in, and I may have already done it by the time this thing airs, but I think we can use a technique similar to what Holly Woodward did to estimate the time it took the megalodon to reach maturity, as well as some of these other fossil sharks. Now, I'm not 100% sure I totally trust the numbers, but I've done some preliminary calculations, and I'm getting an age of around, I want to say 300 or 400 years for it to reach maturity. And of course, if that's true, its lifespan, full lifespan, would have probably been even longer. Am I willing to make some predictions? Yes. And there was a prediction I made at this Creation Research Society meeting last year, where I think you can get good estimates of ages at maturity for fossil creatures from before the flood, and you were to plot them as a function of body mass on a log-log graph, I think you're going to get something very similar, very close to a straight line with a slope of about 0.25. But it's going to lie above the trend line for modern animals. Now, it's going to be hard getting sufficient data to do that, but I think that is a likely consequence of some of this earlier research that's been done, the way these animals scale and their lifespan scale with body size. So that's kind of what I've been working on. I hope this has been an encouragement to you. Hopefully, we won't even have to show you this video because I'll make it on time from the airport. But just in case I didn't, here's a backup copy for that. Thank you very much.